All right, welcome to day 3 of our APStats review. I'm just quickly pulling up on Schoology. I already have our questions. We're going to go over Unit 5 and Unit 6 today. If you look at the two assignments on Schoology for this, Unit 5 is basically, why is my sample not? So introducing statistics like yours. This is your normal distribution, your central limit theorem, biased or unbiased, sampling distribution for proportions, difference of proportions, sample means, difference of means. That's for Unit 5. Unit 6 then would go constructing confidence intervals for population proportions, justifying a claim. So these are your hypothesis testing, setting up a test for population proportion, interesting p-values, and justifying a claim decisions. So one is looking at the distributions, and you generally utilizing the central limit theorem. And then the second part is doing confidence intervals and hypothesis testing. So with that being said, let's jump into our first question. So we have our Unit 5 question on the page. I will pull up a new document so we can actually write on this thing. Do Unit 5. There we go. So it says, researchers are studying two populations of sea turtles. In population D, 30% of the turtles have a shell length greater than 2 feet. In population E, 20% of the turtles have a shell length greater than 2 feet. For a random sample of 40 turtles selected from D, 15 had a shell length greater than 2 feet. From a random sample of 60 turtles selected from E, 11 had shell length greater than 2 feet. Let the proportion, sample proportion, represent the sample proportion for D, and let p hat of E represent the sample proportion for E. What is the value of the difference of p hat of D minus p hat of E? So this is, first part is just setting up the, let's say, 5A. We want the sample proportion for D. So we had 15 out of 40, which I believe is 3.375. The sample proportion for E is 11 out of 60, if I can read that right, which is approximately 0.183. So the difference, I can do that, is 0.375 minus 0.183, which is 0.192. Now it's easy. Part B says, what are the mean and standard deviation of the sampling distribution of the difference in sample proportions? Show your work in detail. So I want the mean, so B, I want the mean sample proportion minus sample proportion E. Well, that's just the proportion of D minus the proportion of E that they gave me before. So if I look back, I have 30% for D and 20% for E. So that would be 0.3 minus 0.2, which is 0.1. Now the standard deviation, if I pull out that formula for the standard deviation for p hat minus p hat E, if you recall, is P1 Q1 over N1 plus P2 Q2 over N2. So I want the sample distribution for these numbers. So this would be the square root of 0.3 times 0.7 over 40 plus 0.2, 0.8 over 60. Now, I trust that you guys can type that into your calculator. And if you get 0.089. So our standard deviation for our distribution. Part C. Can it be assumed that the sampling distribution of the difference of sample proportions is approximately normal? So I want you to think, what do we need to have in order for this to be normal? Well, this is going about checking our assumptions and conditions. Namely, for a, let's say this is part C. Let's do this in a different color. For a normal model, we need to have a random sample, which I believe we are both saying in these cases, people were random sample for both of those turtles. So randomly selected. I would say 40 and 60 turtles are less than 10% of all turtles. So 40, 60, less than 10% of all turtles. Now, if you wanted to double check that, that would mean there would need to be a minimum of 600 turtles that we were checking in order for this to be true for sea turtles. And lastly, we need to check NP and NQ are greater than or equal to 10. So in our situation, we had NP, which is, let's say ND PD, that's 40 times 0.3, which is 12. And then ND QD would be 40 times 0.7, which is 28. Then we have NEPE is 60 times 0.2, which is also 12. And then NEQE, which is 60 times 0.8, it's going to be bigger, 48. Each are greater than or equal to 10. So we can assume a normal model. So this question is going to, can you check the conditions correctly? Part D, consider your answer in part A. What is the probability that the sample proportion is greater than the value found in part A? So this is going more towards how unusual is this? And we should think, if we're using a normal model, that we should be able to calculate z-scores. So as I open up my calculator to do this, let's just think for part D. For z-scores, we have our sample proportion minus our mean difference over our standard deviation. So this is putting all of these calculations together, and then we're going to say how unusual this is. So just filling in the numbers. From part A, the first number is 0.192. From part B, our mean difference was 0.1. From part C, sorry, part D, part B as well, we had our standard deviation is 0.089. Now, I'm just going to jump quickly and say this is 1.03. So that's my z-score. Now, if I'm thinking z-scores, I can use normal CDF. And I want to see what is the probability that the difference is greater than the value you found. So my lower bound is going to be 1.03. My upper bound is going to be some high number. And because I found the z-score, I can just do 0 and 1. Now let's jump to my TI Inspire. Just share that with you guys really quickly. And if I go menu, 6 for probability, 5 for distributions. I want normal CDF. My lower bound is 1.03 because I want to be greater than that. My upper bound is, make it 999. And if I type that in correctly, I see that my probability, let's switch back to my iPad, is about 15%. So the probability that we got this or higher, probability, the sample proportions difference is greater than 0.192, that's what we were comparing it against, is approximately 15%. All right. That takes care of each of those pieces. Hopefully you see that this is looking at building a sampling distribution and then being able to justify that it's a normal model. Once we have a normal model, then we can do our calculations. So let's open up question 2. And then I'll get my notes back up here. Let's do our little dance. So question 2, make this smaller. 5, 2. Let's do this in black. 5, 2. I will read this to you guys, and then we'll get going. Show all your work, indicate clearly the methods you use because you'll be scored on the correctness. The following histogram shows the distribution of house values in a certain city. The mean of the distribution, that'd be pretty good to know. The mean of the distribution is 403,000, and the standard deviation is 278,000. Good to know. We obviously see that the histogram is skewed to the right. But that doesn't necessarily mean that we can't use a normal model. As we've seen, this is a quantitative data, so the larger the sample size that we select, the more likely it is that it's going to be normal by the central limit theorem. Suppose one house from the city will be selected at random. Use the histogram to estimate the probability that the house selected is valued at less than $500,000. So for this first part, if we're thinking about how to go about this, I'm just looking for what's the probability that the value is less than 500,000. So I want to look at this and try to estimate as best as I can everything that is, let's say, underneath those 2 bars. So I'm going to say that the first bar is just below 0.35. So let's say that's 0.34 plus, I think the second one is just a little bit higher in terms of the comparison. So let's say that's 0.37. And it also says estimate. So if I add those 2 together, and I know that they are decimals because this is a relative frequency chart, so I'm just looking at the percentages, that would be 0.71. That would give me the probability that my value is less than $500,000. Now, because estimates are a little rocky, like if you said they were both 0.35, then you could have anywhere between 0.68 and 0.74, and your answer would be generally correct for this. Okay. Part B is probably going to say a sample size. Yeah. So part B, let's make this pen size just a little bit bigger so you guys can see it. Part B. Suppose a random sample of 40 houses are selected from the city. Estimate the probability that the mean value of 40 houses is less than $500,000. So I want you to first think about this. Because the sample size, which is greater than or equal to 30, we can assume that this is approximately normal. So by the central limit theorem, we can use a normal model. With our model being our mean of our population, which is just our mean, or 403,000, that's what they gave us above. Our standard deviation for our sample is going to be our standard deviation over the square root of n. So because we have a sample size of 40, we have to reduce our sample size. Sorry, our standard deviation. So that's 278,000 over the square root of 40. You type that into your calculator, and we will get approximately 43,956. Now, because we have a mean, we have a standard deviation, we're asked to find what's the probability that the average of our 40 is less than 500,000. We could do a z-score, but we could also say this is our normal CDF. Our lower bound is a small number in this case. So I would say 0 to 500,000 with our mean now being what we have, 403,000. And our standard deviation being 43,956. So again, just a different way of showing how to do normal CDF calculations. I'll again go menu on the calculator, 6 for statistics, 5 for distributions, 2 for normal CDF. My lower bound in this case, I'll keep it there. My upper bound is 500,000. My mean in this case is 403,000. And my standard deviation is 43,956. If I hit OK, let's double check. I need to get rid of that comma. I get a probability. Switch back again. Switch back over to my iPad. We get the probability is approximately 98.6%. As we saw, 2 ways of calculating. You could also do z-scores, and that's totally fine. For part C, the following table shows the values in thousands of dollars of 40 randomly selected houses. Calculate the sample mid-range. Now, I know we didn't make a whole lot about this number. So the mid-range is the midpoint of the range. It's kind of puts it together. So we need to look at the low value. I believe the low value is $34,000. The high value is 1,084,123. And then we're just taking that over 2. So this would give you 559,000. And that's C1. C2 says, explain why the mid-range might be preferred to the sample mean as an estimator of the population mean. Well, as you could clearly see, the sample mid-range is much easier to calculate than the sample mean because it only uses 2 values. So mid-range easier to calculate than sample mean. And that's all that's saying. You can see why someone at a glance might want to use the mid-range over the sample mean because they don't want to add 40 numbers divided by 40. Part D. To investigate the sampling distribution of the sample mid-range, a simulation is performed in which 100 random samples of size 40 were selected from the population of house values. For each sample, the sample mid-range was calculated, and recorded on the following dot plot. The mean of this distribution of sample mid-ranges is 617,000 with a standard deviation of 136,000. Based on the results of the simulation, explain why the sample mean might be preferred to the sample mid-range as an estimator of the population. Now I want you to think about this. They did a simulation and calculated the mid-range of each. So in part D, we already, like if you think that this question is building, with a sample size of 40, the sample mean is approximately the same as the population mean, which we said, so the population mean was 403,000. That's by the Central Limit Theorem. The sample mean mid-range was 617,000, which is much larger than the population mean. The sample mid-range is a biased estimator of the population mean, because if we're looking for the mid-range, we're looking at the range of values, and I'm looking at the highest value in that sample, which is going to be more skewed. Also, if we wanted to be a little more specific, the standard deviation of the sampling distribution of the sample mid-range. So if we want to be complete, standard deviation of mid-range, they said was 136,000, which again is much larger than what we saw for the population standard deviation, or the standard deviation we had with the sigma divided by the square root of n, then 43,956, meaning that the sample mid-range is a less precise estimator. So first, it's biased towards the larger values, and two, it's less precise because the standard deviation is wider. It's not as accurate. It's not getting more concentrated like the central limit theorem asks you for. So that takes care of all 4 parts of this question for part 5. So let's move on because we are a little short on time. Let's go to unit 6. Unit 6, question 1. These are going to get more into your hypothesis testing. So let's read. A recent survey collected information on television viewing habits from a random sample of 1,000 people in the United States. Of those sampled, 37% indicated that their favorite sport to watch on television was American football. Construct a 95% confidence interval for the proportion of all people in the United States who would indicate that their favorite sport to watch on television is American football. Okay. So we need to think building a 95% confidence interval. So we need to panic. And actually AP will go with this acronym. They actually prefer it. So our parameter of interest is the sample proportion, sorry, p hat is 0.37. That's what they gave us. Sample proportion for percent Americans whose favorite sport to watch is football. And I mean that in the American sense. Now we got to check the assumptions and conditions. Which is similar to what we did with the unit 5 parts. So we have a random 1,000 people is less than 10% of all, let's say, US adults. And NP, which is 1,000 times 0.37, NQ, which is 1,000 times 0.63. Those are both greater than or equal to 10. So we are justified in using a normal model. So we're going to use a 1 proportion Z interval. So I named the interval. Now I'm going to find the test. It's not really a test statistic, but we need to do our Z interval calculation. So I'm going to write out our interval. So it is p hat plus or minus the critical value times the square root of PQ over N. So my sample interval is 0.37 plus or minus 95% confidence interval, which we can assume is 1.96, square root of 0.37, 0.63 all over 1,000, which gives me 0.37 plus or minus 0.03. So now I get my interval, which is 0.34 to 0.40. And lastly, I'm going to conclude this by interpreting what that means, because it asked me to construct and interpret a 95% interval. So the true proportion of Americans whose favorite sport to watch is football. So I should say 95% favorite sport to watch is football is between 37% and 34% and 40%. And I should insert, we are 95% confident that, and I needed that part. Sorry. Part B. Based on your answer, is it reasonable to believe that 33% is the actual percent of people in the United States whose favorite sport to watch on television is American football? Well, based on part A, 33% is not in our interval. And because it's not in our interval, therefore, it is not reasonable to conclude that percent is accurate. And that's the question. Build a 95% confidence interval and interpret it. So that's the full panic. And then, is this in our interval? No, it's not. So we are kind of done. That was easy. Moving on to the last question. Just go back. 6, question 2. Apologize for the way I cut this up. So that's on the screen. Let's read it to you guys. Fair die, with its faces numbered from 1 to 6, is one which each number is equally likely to land face up when the die is rolled. On a fair die, the probability of the number 6 will land is 1/6. A group of students wanted to investigate a claim about manipulating a fair die so that it favors one outcome. The claim states that if a fair die is put into an oven and baked at 200 degrees for 10 minutes, the inside of the die will begin to melt. When the die cools, the inside will be solid, but with more weight towards the bottom. This shift in weight will cause the face that was up when the die cooled to land up more often than that of the other faces. The students obtained a fair die and baked it according to the preceding directions. The die cooled with the number 6 face up. After the die cooled, they rolled the die 200 times and the number 6 landed face up 43 times. Let P represent the population proportion of the times the number 6 will land up with the baked die if the die could be rolled an infinite number of times. This sounds like building a hypothesis test. Clark, one of the students, constructed a 95% confidence interval for P as 0.215 plus or minus 0.057. Does the interval provide convincing statistical evidence that the number 6 will land face up more often than on the baked die? Wow, that's a lot. So we have to think, in all of that setup, they're trying to say, I gave you the confidence interval. What would we expect? So the confidence interval that Clark built was 0.215 plus or minus 0.057. So I want you to think, the lowest bound, so we can say we can be 95% confident, if I'm just interpreting this confidence interval, that the true proportion of times 6 will land face up is between, the lower bound is 0.158 and 20.272. So that's from Clark's confidence interval. Now, if we take that one step further, because 1/6, which is 0.16667, or 6 repeated, is included in our interval, we do not have convincing evidence. We do not have convincing evidence that supports that 6 will be more likely. Part B. Part B says, Aurelia, another student, suggested they conduct a significance test to investigate the claim. She tested the hypothesis. Her null was p is equal to 1/6 versus p is greater than 1/6 at the significance level of 0.05. She obtained a test statistic, so she got a z-score of 1.83 with a p-value of 0.033. Do the results of the significant test agree with the results of Clark's confidence interval? Explain your reasoning. Okay, so if we looked at Aurelia's, if she says at a alpha level of 0.05, we would reject the null hypothesis because obviously 0.033 is less than 0.05. So with Aurelia's, there is statistical evidence that the proportion will land, that 6 will be more likely. I follow the same language. This does not agree with the confidence interval. This does not agree with the confidence interval. That's the answer. So part C says the two standard normal curves are shown below, one with the confidence interval calculated at part A and one for the significant test conducted for part B. The confidence interval curve labeled the critical value of 95% shaded area below. For the confidence interval curve, label the critical values for the 95% confidence interval and shade the area represented below, values in 5% outlier. I'm guessing we're going towards a error test. Okay, so for our confidence interval, what we are saying here is we are 95% confident, and then the place that we are looking elsewhere is here and here. And both of those are 2.5% above and below because confidence intervals are a two-tailed test. What she did in the other test is that, and we should say this is what, 1.96 on our standard normal model, 1.96. Here, she had one-tailed test with an alpha level of 0.05. So this is 95%. And this portion is 5%, with this critical value being 1.645, which is a 90% confidence level. Joaquin, a third student, noted that the confidence interval in part A gives plausible values of the parameter as an interval between two values. He suggested that they develop a one-sided confidence interval because they were only concerned with whether the number 6 was landing face up more often than expected, not less. One-sided confidence interval L, such as plausible values for the formula, is p hat plus minus z star. So sorry, it's plus. Determine the values of Z star needed to create a one-sided 95% confidence interval. And so for this, in part one, we went from negative 1.96 to 1.96. That was our 95% confidence interval. For a one-sided test, it's it's 2 alpha, so it's a 90% confidence interval. If you do a 95% confidence interval, you get 1.645. So for part D, because we want a 95% confidence interval with no upper limit, the critical value is the boundary that separates the smallest 5% from the largest 95%. So our critical value is going to be negative 1.645. Therefore, the lower bound is 43 out of 200 plus negative 1.645 square root PQ over N, which is approximately 0.1672. So according to our one-sided interval, we can be 95% confident that the proportion will land face up is greater than 0.1672. So because 1/6 is not contained in this interval, the results agree with the significance test in part B. The one-sided confidence interval is equivalent to a one-sided significance test. And that is how you build to something that we had not discussed. So hopefully this helps you in our practice. I really encourage you guys to do these on your own before you watch me do it. We will finish up tomorrow with unit 7, which has our chi-squared and inferential statistics on 2 variables. And then I will open it up if anyone wants to come to class on Friday at the end of this week to ask any questions. All right, one more. I'll see you guys later.